Hey students, in today's lesson what we're looking at is fission and fusion. So the main aim of this particular presentation is to get you more familiar with the binding energy equation, E equals mc squared, and then towards the end we'll start looking at how fission is used to produce energy. That should cover pretty much all of the syllabus points on nuclear physics. So we'll start off by answering the question that what is fission? So generally speaking, fission is when a nucleus will split into two or more pieces, and that typically happens or is triggered when a neutron is absorbed by that nucleus and then it becomes unstable. Okay, so as a bit of a warm-up into this topic, let's look back at those radioactive decay equations that we were solving a couple of weeks ago, and now we're going to apply the same principles of conserving the mass number and the charge number and finding the element using the periodic table. We're going to use those same skills to actually help complete nuclear equations for fusion reactions. So if you have a look at the screen, you can see that we have a neutron interacting with the uranium nucleus, and then two products are formed and a certain number of neutrons. So knowing that, can you solve for the unknowns? I'll give you, as long as you need, just press pause and I'll start the answers soon. Okay, and here are your answers. I hope you did well. Okay, so what I've got on the screen is a fairly straightforward fission reaction where you have a neutron interacting with that uranium atom and then producing baryon, krypton, and 3 neutrons. It's a fairly standard fission reaction. So without getting you to do too much, the first thing I'm going to ask you to do is, if I was to tell you that there was a loss of mass, so when these new particles were formed, if we were to look at the mass of those products, we find that there's a difference or a loss of 0.215 atomic mass units. Could you from there calculate how much energy would be released from that fission reactions? So the easiest thing to do will be to work it out in electron volts first, but I want you to, and eventually I want you to do both. So give that a go. Okay, so I'm assuming that you've had a crack at it. So if the first thing we want to do is, if we know the change in mass is going to be equal to 0.215, then we can answer this one pretty quickly to get mega electron volts, right? So that means your energy is just going to be 931 multiplied by 0.215, and that's going to be 200 mega electron volts. Now, to get it in joules, there's a couple of ways you can do it. You can simply convert this number if you like, as we did, as we've shown before. But what I like to do is actually convert it to kilograms first, and then use E equals mc squared. So the change in mass is going to be 3.569 times 10 to the negative 28. If you multiply U by 1.66 times 10 to the negative 27. So what you'll end up getting is E equals mc squared. And that's going to be equal to 3.569 times 10 to the negative 28 times 3 times 10 to the 8 squared. And you've put that in your calculator, and what you should end up with, if everything goes well, is 3.21 times 10 to the negative 11 joules. So now that I've given you the mass difference, and then from that you've told me how much energy is released, I want you to start from scratch. So I've given you the reaction here. So we have a neutron interacting with a uranium atom, and it's producing xenon and strontium and 2 neutrons. These are your masses that you need to use. Notice that I've given you the mass of a neutron to be corresponding to what it actually is in the data sheet. From here, can you calculate the amount of energy released by the fission reaction? Go. Okay, and to solve this, all we're doing is we're finding out the mass difference, so it's pretty straightforward. We've already done it for you on the computer. We've got the mass here of that uranium atom and the neutron, and then on top of that, we are subtracting the mass of xenon and the mass of strontium and the mass of those 2 neutrons. So once we've done that, we can get a mass difference of 0.19723 atomic mass units, and then you just simply multiply that by 931. Because the question hasn't asked you to calculate it in joules, you don't need to. So there's your answer. Now this question is in 4 parts. It's a typically challenging one, so the students in the class are often stumped by the time they get to the end. So let's start it off nice and easy. We've got ourselves an equation here. We've got ourselves the masses. The whole thing's in kilograms. The first step is asking you to find out what is the decrease in mass of these particles after the fission reaction. So to solve this, what we want to do is just find the mass defect the same way, or the mass difference the same way we would find it in any other time. So we have the mass of the neutron, 1.67495 times 10 to the negative 27. And we're going to add onto that the 3.90305 times 10 to the negative 25. And we're going to subtract from that the mass of the products. And the mass of the products being the mass of the barium, and the mass of the krypton, and the mass of 3 neutrons. If you put that in your calculator, what you should get is 3.10 times 10 to the negative 28 kilograms. So the thing about this question is that it's actually fairly easy. You would have known what you were doing the whole time, but where people seem to become unstuck is actually entering in these really long numbers into their calculator. That's a common spot for mistakes, so just make sure that you get to know your calculator. Get a calculator that you'll be taking all the way through to year 12. So as I've spoken to you about it before, get a calculator that can solve quadratics, so it's year 12 ready. And you should, with further and further practice, you'll make less and less calculator mistakes. So the next question, or the next part of this question is, if you know the decrease in mass, can you now tell me how many joules of energy are released during the fission of this nucleus? Again, it's pretty simple at this point, isn't it? So you just use your E equals mc squared, and that's going to be your 3.10 times 3 times 10 to the 8 squared, and if you put that in your calculator, you should get 2.79 times 10 to the negative 11 joules. So with this answer, there's a couple of mistakes that could have been made here. One of the more common ones is that you put this square in the wrong spot, or you evaluate it incorrectly on your calculator. Another place that you can inadvertently lose precision in your answer is, it's not really too applicable to this one because this was 3.10, it was pretty close to 3.10. But if you give an answer in 3 significant figures in the previous part of a question, and you then need to use this answer in a part B or a second part of the question, what you really want to try and do is keep as much precision as possible as you carry that number through. So again, this comes with getting to know your calculator. You can set numbers to specific variables, or you can use the answer function just to maintain that precision all the way through your calculations. Remember, you still need to give your final answer to 3 significant figures, but if you're going to use that in a follow-up calculation, you want to use as high a precision version of that number as possible. Okay, so part C is sort of one that some people get a little bit unstuck on. It's asking simply to express the decrease in mass as a percentage of the mass of the initial nuclear particles. Give it a go. Okay, so in this question, it seems a little bit funnily worded, but it's not as terrible as you might think. All you need to do is first find out what the mass of the reactants are. And that's just going to be your neutron. Plus your uranium. And what you should end up with is 3.9198 times 10 to the negative 27. No, negative 25, sorry. Kilograms. So this is the mass of those reactants. And just you want to express that as a percentage of, you want to express the mass difference as a percentage of this particular mass. So you just get what you have at the top there, the 3.10 times 10 to the negative 28, and divide that by your 3.9198 times 10 to the negative 25. And don't forget to multiply that by 100 to get it as a percentage. And if you put that in your calculator, what you will end up with is 0.0791%. The point that we're making here with these questions that we've got is that, for starters, the amount of energy that's released in one fission reaction is actually quite small. It's times 10 to the negative 11. But remember, this is one reaction. And the difference in mass is 0.0791%. So the decrease in mass is also very, very tiny. But as the next part of this question will demonstrate, this is actually a huge amount of energy, relatively anyway. Okay, so part 4 of this question is a bit more tricky. It's asking that if you have 5 kilos of uranium-235 and it completely underwent fission, how much energy in joules will be released? So if we were looking at that objectively, we've got a certain amount of uranium up here. We've got 5 kilograms of uranium-235. Knowing that, if it all underwent fission, how much energy in joules would you get from that 5 kilogram bunch? Something to keep in mind is that this neutron that we have here will kick off the process, but what we can assume is that these neutrons that are produced at the end, or as products of the initial fission reaction, they will go on to initiate the reaction for the follow-on uranium atoms. So you know that you only need one neutron to actually kickstart this entire process, and a chain reaction starts. And we'll talk about that later on. So have a crack at that question. If you have 5 kilograms of uranium-235, knowing what you've calculated so far, you might need to calculate a couple of other things. How much energy would be released? Knowing that you have 5 kilograms, you first need to figure out how many uranium atoms is that, right? So first question I want to ask is, how many uranium-235s do I have? And that's just going to be equal to your 5 kilograms divided by the mass of uranium-235. And if you put that in your calculator, what you end up getting, as you'd expect, a very large number, is 1.281 times 10 to the 25 atoms. So we have a very large number of atoms. Again, it's 5 kilograms, it's what you'd expect. But from this, we can determine that we've got this many number of reactions, because if we have 1.281 times 10 to the 25 atoms and they all undergo fission, then this is how many reactions we have, because we only have one atom required per reaction. So all we need to do now is, well, we know that per reaction, the energy is this number here, the 2.79 times 10 to the 11. Negative 11, sorry, joules. So the energy is going to be that number, 2.79 times 10 to the negative 11 joules, multiplied by the number of reactions that take place. And put that in your calculator, you should get 3.57 times 10 to the 14 joules. And I'm sure you would agree with me that that is a massive number, considering we're only using 5 kilograms of fuel. Okay, so with this next example, what I'm going to do is illustrate just how much energy you can get from fission reactions using a real-world example. So I'm going to continue on from the last example. We're looking at that same uranium fission reaction, and I've carried over some numbers that we worked out in the previous question. So the question that I'm now asking is, if you build a nuclear reactor and you use that uranium-235, how many fission reactions per second are going to be required to power my PlayStation 4? So the PlayStation 4 that I've got, it tells me it's 110 watts. So something that you may or may not know is that power is equal to the change in energy, or the energy consumed, or basically energy divided by time. So if I've said to you how many fission reactions per second are required to power my PlayStation 4, which is 110 watts, well, 110 watts means 110 joules per second. So knowing that every second my PlayStation 4 requires 110 joules of energy, how many reactions am I going to need for that to happen? So starting with the equation that I've given you, power is going to be equal to energy over time. So we know that the energy required per second is going to be 100 joules. And if I know the energy for one reaction, which we calculated in the previous slide, is going to be 2.79 times 10 to the negative 11 joules. From here, I can then just figure out, well, how many reactions do I need? Well, I need 100 joules. So how many times does 2.79 times 10 to the negative 11 fit in there? And what I will get is 3.94 times 10 to the 12 reactions per second. And at this point, this may not mean anything to you. That's a lot of reactions per second, but it doesn't really tell us much. But let's look at the bonus question. So if we know that every second I need to have 3.94 times 10 to the 12 reactions, or fission reactions occurring, can you tell me, firstly, you want to figure out how many reactions is that per year, or 50 years in this case, and then translate that to a number representing how much uranium is going to be consumed. So the question's asking how much uranium is needed to power my PlayStation 4 for 50 years. Okay, so this question can be answered in a number of different ways. So if you got the answer using a different method, then I'm sure that method was valid. So the first thing you want to do is you want to figure out, okay, what is the mass of uranium-235? I'm just going to rewrite it. The mass of U-235 is going to be, it's up the top there. It's 3.90305 times 10 to the negative 15 kilograms, right? Or 25 kilograms. So this is how much one atom is. So if I'm going to need that many reactions per second, so the amount of mass that I need for 1 second is going to be equal to that number multiplied by the 3.94 times 10 to the 12. And what I should get if I do that is 1.53 times 10 to the negative 12 kilograms. So that number there represents how much uranium I'm going to need for 1 second. Still, this doesn't really tell us anything interesting about how much uranium we're going to need. So what we do is we amplify the problem and say, okay, well, how long or how much will I need for 50 years? Okay, so the mass that I need for 50 years is going to be that number again, the 1.53 times 10 to the negative 12. And that's for 1 second. If times it by 60 to get it for 1 minute, times it by 60 again to get it for 1 hour, times it by 24 to get it for 1 day, and times it by 365.25 to get it for 1 year, and then multiply it again by 50 to get it to 50 years. So multiply it by a lot of numbers, and if we do that and chuck it in our calculator, what you should end up with is 2.4 grams. And hopefully now you can see just how much energy you can get from a fission reaction. So you're powering a PlayStation for 50 years with just 2.4 grams. How cool is that? Right, so now that we've done fission, we've done a few fission reactions, we're going to look at fusion now. So fusion is effectively, I guess you could say, the opposite of fission. So in fission, when you have a heavier nucleus breaking up and forming different pieces that are smaller. In this case, you have small pieces forming a heavier nucleus in fusion. We'll talk about, we've already spoken in binding energy about why this occurs in lighter elements and why fission occurs in heavier elements, but we'll readdress this later on. What I want you to do first is just the same as you did with the fission reactions, is I want you to find all the unknown quantities in these reactions. Okay, and the final calculation for this presentation, much the same as you've done for fission reactions, is to calculate for me the amount of energy released by the fusion reaction. It is the exact same process. You find the difference in mass and you calculate the energy that corresponds to that missing mass. Okay, so what you should have done is just worked out what the mass of the reactants were. So you've got your deuterium there, and you've got your tritium here, and you subtract the addition of the helium-4 and the neutron, which are the products in this reaction, and you should have got a mass difference of 0.021524. We've got that in Joules. I haven't asked you to give me the answer in joules, so all you would have had to have done is multiply that answer by 931 to get the final result, which is 20 mega electron volts. So as you can see, the solving for the energy in a fusion reaction is exactly the same as solving it for the fission reaction. But something interesting that is in the syllabus that you sort of need to know, looking at this slide here, is that the difference in energy that you see between products of fission, so from going from uranium to the lighter elements, the difference in that energy isn't terribly huge. But when you go, say, from hydrogen and deuterium and tritium to heavier elements like you've got the helium all the way up here, the change in energy, binding energy per nucleon, is actually quite huge. So what this means is that the amount of energy that you get in a fusion reaction per fusion reaction is much higher than what you get for fission. So I think we've seen some videos already where the fusion is obviously the most preferred way of making energy, but the problem with fusion is that we need super duper high temperatures and super duper high pressures to actually make those reactions happen, and that is the problem that we faced for decades. So that's all we've got in terms of the presentation. What I'll do now is put on an interactive for you to observe a couple of things. Okay, so this is the interactive that I've linked on the website for you. This is from FET. It's fairly old. It's a Java one, but it's still really good. It sort of helps you understand what's happening with fission. So the first screen that you see is you have the nice little uranium atom sitting here. The whole thing's just wiggling around. It's a little bit radioactive, but then you throw a neutron in the mix. The neutron is absorbed. It's important we talk about how the neutron is initially absorbed, and then the atom becomes very unstable and then undergoes fission. So you can see it becomes unstable and then divides up into those daughter nuclei. So moving on from that, we want to talk about how we have a chain reaction. So again, if I fire that neutron at the uranium atom, you have the pieces come off, the daughter nuclei come off, as well as extra neutrons over there. So what I want to do is I'm going to add a number of uranium nuclei, and then what you'll see is those neutrons that are released are going to trigger more fission reactions. Now, lucky for me, I had enough uranium atoms in there for the chain reaction to occur. And when we have enough of that fissile mass, we call that having the critical mass, or having a mass above the critical mass. So the definition of critical mass is the amount of fissile material required to sustain a chain reaction. Another important thing that I should probably point out now is that if I reset that and hit it again, you notice that when the neutrons are released, they're going they're released with the energy corresponding to how much energy is released from a nuclear reaction. So it's going to be fairly fast. One of the important things here is that for fission to occur, you need to be able to slow down these neutrons. If they're going too fast, then they'll just essentially bounce off and not be absorbed, or the neutron capture won't occur. So what you typically have in a nuclear reactor is a moderator, and the moderator is usually water. And what that does is that slows down the neutrons. So when it's released from that uranium atom, it won't be traveling so fast, and it will be fairly useful. And finally, we've got a simulator of a nuclear reactor. So what I can control here are the control rods. Now, control rods are basically neutron absorbers, right? So when you have neutrons being released in this chain reaction, they won't be able to go very far if you've got the control rods in the system. So if I fire some neutrons, what you notice is that the reactions won't cross over, that those rods will absorb the neutrons, and the reaction will stop fairly quickly. But if I'm just going to reset it and then pull out the control rods, what you'll find is those neutrons will continue to trigger further nuclear reactions, and you'll have that chain reaction taking place to the point that you have plenty of energy coming in. And you see the temperature increases. So if I throw in those control rods now, it's probably going to be too late. Yep, it's definitely too late. But those control rods, usually they moderate how quickly the reactions are taking place using those control rods, which just they capture the neutrons so the uranium atoms can't. And that's essentially the end of this week's lesson. What I want you guys to do is just finish all the problems in the textbook, and I'm sure the book has plenty more to read on nuclear reactors and chain reactions. The focus of my lesson was to get you to apply those binding energy calculations. All right, thanks.